We're going to do this question here, which is an example of using some vector calculus. I guess first of all, with a vector calculus, if we've got some vector expression with the I component, with a expression in terms of t for the I component, expression in terms of t for the j component, an expression in terms of t for the k component, we can differentiate the vector expression by just differentiating each of the components separately. So dr dt will just be f derivative t of the I component plus g derivative t of the j component plus h derivative t of the k component. So that will be our differentiation going that way. And of course we could go backwards here and integrate to get back to the original function. Remembering, however, that for each of the components, the I, j and k component, when integrating we'd have a constant of integration, so a plus c1 plus c2 plus c3 here. Okay, so let's have a look at the question. We've got a particle initially at rest at a point with a position vector 2j meters, and t seconds later we're given an acceleration given by this vector expression here, 8 cos 2t I plus 2j. So first thing we're after is an expression for the velocity of the particle at time t. So to find our velocity, we can simply integrate the acceleration. So it'll be the integral of 8 cos 2t I plus 2j dt. So integrating this, we can just integrate each of the components separately. So cos 2t will integrate to 4 sine 2t. And don't forget the constant of integration, c1. That's our I component. And integrating 2j, we'll get plus 2t. Whoops, and I forgot the constant of integration there. Let me sort that out. Plus c2 of j. So there's our expression for our velocity. Now we can work out these constants of integration by looking back at the original question. Now initially it's at rest, so it means initially we've got a velocity of 0. So we can go ahead there and give the expression as well. When t is equal to 0, sine 2 t will be equal to 0. So we want this c1 value to be 0 as well. So that's going to go to 0. We're left with 4 sine 2t I. And same goes over here. We want the j component to be 0 as well because the particle is at rest initially. It'll be 2 times 0 is 0. We want this c value here to also be 0. So we've got plus 2t of j. And this intermediate step here, we could probably just about leave that one out because we know it's at rest. Okay, so that's part A of the question. Part B, find the value of t greater than 0 when the particle is first travelling parallel to the y-axis. Okay, so perhaps a little diagram here might help. So if the particle's travelling parallel to the y-axis, so moving in this direction, velocity either that way or perhaps in the other direction. And we can see when it's moving in that direction, the velocity of the I component will be 0. So in this direction, it hasn't got any velocity. So what we can do in this case is look at the I component and just set that equal to 0. Because it's moving parallel to the y-axis at this point, just set the I component equal to 0 and solve. So solve 4 sine 2t is equal to 0. And we want t greater than 0. So solving that, we'll just get sine 2t is equal to 0, pi, 2 pi, etc. 2t is equal to 0, pi on 2, pi, etc. So the first time that it's travelling parallel to the, what have I done there? Oops, that should have been 2t at this point. There we go, so we got 2t is equal to 0, pi, 2 pi, and t therefore is equal to 0, pi on 2 or pi. So the first time after t is equal to 0 that we've got the particle moving parallel to the y-axis will be t is equal to pi over 2 seconds. Okay, so that's that part done. And the final thing here, we want an expression for the position vector of the particle at time t. So now we're after the position vector. So we're going from the velocity vector here, and we want to integrate that to get our position vector. Okay, so let's have a look here. So we'll have our position vector, t, will just be the integral of both the I and the j component. So the integral of 4 sine 2t I dt plus the integral of 2t j dt. So we're just integrating separately the I component and the j component. So that's pretty straightforward. We'll get negative 2 cos 2t. Don't forget the constant of integration, so I'm going to call that C1. There's my I component. Plus this one here will integrate to 2t squared over 2, or if you like, just t squared. And again, plus C2 times the j component. We can now go back and have a look to see what was happening initially. So initially it was at rest, but it had a position vector of 2j. So over here I'll just put 0, the initial position vector was 2j. So we can use this piece of information here to work out our constants of integration C1 and C2. And this position vector of 2j is effectively 0i plus 2j. So first of all, for the I component, we want this I component being equal to 0. Now, got to be a little bit careful here, because you might think, okay, I component is 0, this C1 must be 0, but incorrect, because this is cos instead of sine. So we require, let me see here, require negative 2 cos 2t plus C1 being equal to 0. And that's at t is equal to 0. So we've got negative 2 cos 0 plus C1 is equal to 0. Now cos 0 is equal to 1, so therefore we've got C1 being equal to 2. Okay, and then of course over for the j component here, we want, when t is equal to 0, we require the j component to be equal to 2. So at t is equal to 0, we require t squared plus C2 is equal to 2. In other words, 0 squared plus C2 is equal to 2. C2 is also equal to 2 there. So there, finally, once we've got all that, we can now go and write our final expression for position vector, which will be negative 2 cos 2t plus 2. That's our I component, and plus our j component, which will be t squared plus 2j. And that's our final answer.